Hello everyone. So in today's lesson, we're going to go over percentage compositions and empirical formulas. Before you begin, I'm hoping that you've had a chance to look at the lesson on the moles, have practiced a bit, and are asking questions. We will come together and answer some of those questions if you haven't already asked at a later time. So let's continue with this lesson. So when we look at or talk about percentage compositions, we can look at different things, different mixtures of things. So we look at clay here, a pizza, the composition of these eggs and based on their different colors and sizes. Then a milkshake, how much of it perhaps is milk or ice or fruits or sugar. The composition of this desk in this drawer here. So paper clips, pens, scissors, a light, a torch here, and a pizza. So ingredients. Water, flour, tomatoes, cheese, all of these five pictures here have percentage compositions based on their individual ingredients, right? And they're going to be similar for similar items. So this clay here or anywhere else in the world is going to have a similar amount of water to clay. Or this pizza made the same way somewhere else will be the same as another pizza made using the same ingredients and same recipe. They'll have the same proportion of, let's say, tomatoes, or same proportion of dough, or water, or salt, or cheese. Now, how you relate that then to chemistry is the percentage composition by mass of a substance like CO2, carbon dioxide, and ammonia, and H3. If we look at their molar masses, now we've talked about molar masses, we can refer to that now. Carbon here has a molar mass from your periodic table of about 12 grams per mole, and oxygen is about 16 grams per mole. Now there are two oxygens, right? And there are 12, there's one carbon at 12 grams per mole. You add them all together, you get a molar mass of CO2. Now, based on its individual mass, okay, so let's add this together. So 32 for oxygen, and we have 12 grams per mole for carbon, for a total of 44 grams per mole. Now, just carbon, contributes 12 grams per mole of a possible total 44 grams per mole. Now we divide these, multiply by 100, and we get a percentage that carbon contributes, and that is 27.3%. Oxygen contributes the majority of its mass at 72.7%, right? And this is the percentage composition of CO2 for the individual elements. Ammonia, similarly, 82.2% nitrogen and 17.8% hydrogen by mass. Right, so that's essentially percentage composition of these two substances. Now, this follows a certain proportion, and that follows the law of definite proportions, where one compound will have the same proportions by mass, no matter where it is. Okay, and we measure this in the form of mass, in grams, and we'll get to that right now. Okay, so let's look at another example. Calcium carbonate. You may be familiar with this. It is chalk, essentially, just not compressed into a nice looking piece of chalk. So for our first step to figure out the percentage composition of calcium carbonate, we're going to take all the elements, all the atoms inside calcium carbonate, and figure out the molar mass of calcium carbonate. Right. So a bit of practice from our previous lesson. One calcium atom has a molar mass of 40.08. Since there's only one, that's a total contribution of 40.08. Carbon, not copper, carbon. There is just one of them, so we have one. Each one has a molar mass, here I'm being a bit more specific here, of 12.01 grams per mole, so that has a total contribution of 12.01. Oxygen, though, there are three of them, right? Three of the oxygens. So 3 times molar mass of 16 grams per mole for a total of 48. We add all of these together and we get a total molar mass of 100.09 grams per mole. And so that's the molar mass of calcium carbonate. Now we're going to find the percentage that the total, or of the percentage that each element contributes based on the total mass. So for calcium, we have a total contribution of calcium that is 40.08 of a molar mass 100.09. Divide these two, multiply by 100, and we get a percentage that is 40.04% calcium by mass. We'll do the same thing with carbon and oxygen, we get these percentages. So carbon contributes 12 grams per mole roughly, oxygen 48, divide by the total, and we get these percentages. So by mass, each of the elements in calcium carbonate contributes these different percentages. And that is then your percentage composition. We can double check, and we should get that all of these will add up to 100%, and sure enough they do. Or at least for some questions you might do, they might come really, really close to it, 99.98, 99.9, so it should add up to approximately or very close to 100%. Okay, next, this example says, a compound was decomposed into its elements. So here we're not given a formula. Our formula is missing. So it says a compound was decomposed into its elements, and we get 10.2 grams of magnesium, and we get 29.8 grams of chlorine. What is the percentage, the percent composition? Okay, let's start. So first we're going to find the total mass of the compound. We only have these two elements, so all we do is we take these two and find our denominator. Right, 10.2, 29.8, add them, we get 40.0 grams. So 40 grams is the mass of the element, or is the mass of the compound. Now, if we're going to find how much each of them contributes to it, you're going to treat this as if you're figuring out your percentage mark on a test. What could you have gotten of a total of 40? What could you have earned? And what did you actually get? Now, I'm sure they're not going to be these numbers or these percentages. You can do better than that. It is then, so for magnesium, 10.2 grams is the portion that magnesium contributes. Of a total mass of 40 grams, divide those, multiply by 100, we get 25.5%. Do the same thing. Well, these subscripts are kind of in the way here, but we do the same thing. 29.8 grams divided by 40, we multiply that by 100, and we get, go back, it's being hidden here, but we get the remaining. So 25, 74.5. I'll write that down. So 74.5%. And we add those together, and that will give us 100%. Okay, so that is the idea behind percentage composition. Now that leads to something. It leads to an empirical formula. We'll show you how. But first, before we make a connection between the two, let's look at what an empirical formula is. An empirical formula is just the simplest form of a chemical formula. So here are two very different substances. Here we have ethene, or C2H4, and here we have cyclohexane. You don't have to know those names. That's for next year. C6H12. Right now, in their simplest form, if you want to think about this in math, if you want to factor these, they will all simplify to this basic proportion. So for every one carbon atom, there are two hydrogens. For every one carbon, there are two hydrogens. If we divide C2H4 by 2, we get this. If we divide C6H12 by 6, we get CH2, right? Our simplest proportion. For every one carbon, we have two hydrogens. This would then be our empirical formula. Not the actual formula. It's definitely not the actual molecular formula. It's just the empirical one in its simplest form. So, which of these are an empirical formula? Okay, so here's where you can pause, hopefully, this video and ask yourself, is 1, 2, all the way to 6, are these, and I know that the last one's being blocked here, we'll end up having to skip this, but are 1 to 5 empirical formulas, yes or no? Okay, and if it's not, so if no, what is the empirical formula? So Fe2O3, yes or no? It is. Yes, it is the empirical formula. This cannot be simplified. You can't divide this by anything and still get whole numbers. Next, C2H6O2. It is not an empirical formula. We can simplify this. If we divide it by 2, we would get CH3O. Continuing, H2SO4. It is an empirical formula. It may look like you can for a moment divide by 2 here, by 2 here, but notice sulfur, there's an imaginary 1 here. You can't divide that by 2 and still get a whole number, so that is an empirical formula. Okay, K2C2O4. We divide this by 2, divide that by 2, divide that by 2. Does it work? Turns out you could do that. That means it is not an empirical formula. The empirical formula is KCO2. All right, last one for us. You can do this yourself in the posted notes. C6H12O3. So can we divide this by a number and still get whole numbers? The answer is yes, we can. Therefore, it is not an empirical formula. Because we can, it's going to be C2H4O as your empirical formula. Okay, moving on. A bit more practice. How many of the following pairs have the same empirical formula? Okay, so analyze E6, K2, CR2O7, K2CR04. Do these have the same empirical formula? If you divide them by the same number, do they have the same empirical formula, or are they even similar to each other? Okay, take a minute, try to go through these, do them yourself, pause the video, and in a moment I'll show you the answers. Okay, so those are the ones that have the same empirical formulas. So notice that one, they're simply not related. These, if we divide, if we divide this by 2, we get that. If we divide this by 5, we get this, right? Do one more. Well, we can't really divide this one. This looks like it is our empirical formula. Here, though, if we divide by 2, right, divide this by 2, we'll end up with that, right? So they do have the same empirical formulas in this one as well, number 6 too. Okay, so in the last type of question we're going to do today, right now, is you're going to find an empirical formula. And this is where we're making a connection between percent composition and our empirical formula. So the connection is that we can determine mathematically what the empirical formula of a substance is based on the percentage composition. And that's what we're going to do now. So an inorganic salt is composed of, we have percentages here, so 17.6% sodium, 39.7 chromium, 42.6 oxygen. Okay, again, so we don't have our empirical formula. We just know that there is sodium, chromium, oxygen in these percentages. Now, what is the empirical formula? So we're looking for, now it could be in a certain order, usually metals are written first. So what subscript would go here, what subscript would go there, and what oxygen would go there? Or what number of oxygens would go here, what number of carbon there, and what number of sodiums there. Okay, that's what we're figuring out. So first and really important step, assume 100 grams. Okay, this math trick here makes this question a lot easier to solve. You didn't have to choose 100 grams, but you'll see that it's going to be a lot simpler. Why? Because if you assume that the mass sample is 100 grams, then that allows you to make this conversion without thinking twice. So 17.6% of 100 grams is 17.6 grams. 39.7% of 100 is 39.7. See how easy assuming 100 grams makes the beginning of this question. So this is really important. As always, assume 100 grams. Right? So now we have individual masses of these substances. Right? Okay, now this is going somewhere. Step 2. We're going to take those masses and we're going to convert them into moles. To do that, we're going to use our molar masses. This is using a factor label method that we also had a short lesson on a little while ago. So we have 17.6 grams of sodium from our 100 gram sample. We're going to divide that by its molar mass. Notice how grams cancel out and we're left with moles. We get 0.766 moles of sodium in this 100 gram sample. And we're going to do that with the rest of them, chromium and oxygen as well. Right, divide by molar mass, grams cancels out, and we're left with those number of moles. And we'll do the same thing for oxygen. We then have 2.66 moles of oxygen. Okay, so now we have all of these. So you can begin to say, right, well, we have a certain ratio now. They're not whole numbers. They're not quite ready to put into a chemical formula. We could say, though, that we have 0.766 sodium as our subscript, but this doesn't really look good. It doesn't really make sense. So there is one more thing we have to do, but we at least have a certain proportion set. right? This is not the right answer, but this is what we're trying to work towards. How can we convert these decimals? How can we convert these decimals into something that makes sense or that is familiar? Okay, and the trick here is we're going to divide by the smallest number of moles. So find the value that is least. So that would be this. That would be chromium. So 0.763, and we're going to divide each of these, this and this and this, by that value. That's forcing everything to become a whole number, or at least close enough to a whole number that we can then round. And this is what happens. I'm going to exit this presentation mode because this part I don't want you to just skip over. I want you to see, and these subscripts are kind of in the way. So I'm going to exit this right now. Might just take a minute. Don't want to keep annotations. No, I'm going to discard that and go back to that slide. There we go. So here we have 0.766 divided by 0.763. What's important for this step is you can round, right? Rounding is okay. So feel free to round at this step. You're going to get really close to 1, round it to 1. One number divided by itself is 1, so that's pretty simple. And here we have 2.66 divided by 0.763, and we get 3.5, right? So not the answer, not the whole number we were looking for, but we can fix this, right? We can fix that. Moving on, I'll go back to presentation mode because we're almost done. Okay, we'll skip over this, right? We saw that. So we have an almost completed empirical formula. The last step is, if we don't have a whole number, we're going to multiply the subscripts, 1, 1, 3.5, by a factor that gives you the whole number. Now, it doesn't mean we're going to multiply this by 50, right? We're going to multiply it by a number that will give us the lowest possible value for these subscripts. So try 2. 2 means that the 1 gets multiplied by 2 and becomes a 2. The 1 here gets multiplied by 2 and becomes a 2. This 3.5 gets multiplied by this 2, and we get 7. This is in lowest terms in terms of the numbers here, and we get our empirical formula. This is then our answer. Perfect. So going back to our food examples, if we have a recipe that asks for 1 egg, 1 cup, let's say, 1 cup of water, and I don't know, this looks like, what is that, 2 cups? Let's just say 1 because it's in 1 cup. 1 cup of flour. If you want to double that recipe, it would then be 2 eggs, 2 cups of flour, 2 cups of water, and 2 cups of flour, right? That's all we're doing here. We're taking a subscripts that, in this case here, 3.5, are not whole, multiplying it by 2 to make them make more sense, to make them look like the empirical formula in the form that we desire. Right, here is your home fun. Practice it. Let me know if you have any questions or any issues. Until next time.